When you press a button on your remote, you are not sending a signal through the air in the way intuition suggests. Instead, you initiate a precise mechanical sequence that closes an electrical circuit. This action triggers a microcontroller to encode data into binary pulses. These pulses then modulate a high-frequency carrier wave before being emitted as invisible infrared photons. The entire process occurs within milliseconds. After that first surprise, we can slow down and trace the mechanism behind what happens when you press a TV remote button. From the first physical step, so the effect stops feeling mysterious and starts feeling engineered. When you press a button on your television remote, the first physical event is the mechanical actuation of the conductive rubber dome. This flexible component sits between the plastic keycap and the printed circuit board beneath it. As you apply downward force, the dome compresses until its inner carbon-coated surface makes direct contact with a specific copper pad on the circuit board. Think of this action like closing a simple light switch in your home wall, but at a microscopic scale within the remote housing. Without this physical compression and subsequent metal-to-metal connection, no electrical current can flow through the internal pathways. The circuit remains open until that precise moment, when the conductive material bridges the gap between 2 points on the board. This mechanical closure is the necessary prerequisite for any electronic signal to be generated or transmitted wirelessly later in the process. Pause 0.8. When you press a button on your TV remote, the internal microcontroller does not simply detect a single closed circuit. Instead, it scans an organized grid of rows and columns to identify exactly which intersection was activated. This matrix scanning method allows dozens of buttons to share wiring paths without creating electrical conflicts. The chip applies voltage sequentially across each row while monitoring column lines for any change in current flow. For example, pressing the power button closes a specific connection between row 3 and column 5 on the printed circuit board. As the microcontroller scans row 3, it detects a voltage drop at column 5, pinpointing the exact location of your press. This systematic approach eliminates ambiguity by isolating each possible button through timed electrical measurements, rather than individual wires. Once the intersection is identified, the system prepares to convert that physical input into a digital signal for transmission. Pause 0.8. When you press a button on your remote control, the internal chip detects which specific key was activated through measurable voltage changes. This physical action must then be translated into machine-readable binary formats that the television can process and understand. The microcontroller inside the device assigns a unique numerical code to each button function, such as power or volume adjustment. These numbers are converted into sequences of zeros and ones using standard encoding protocols like NEC or RC5. A complete data packet is assembled by arranging these binary digits into a structured frame with start bits, address codes, and command values. For example, pressing the power button might generate a sequence beginning with a specific header followed by the binary representation of the device address and the on-off instruction. This organized collection of bits ensures that the receiving television can distinguish between different commands and identify which device is being controlled. Without this precise encoding structure, the signal would be indistinguishable from random noise or interference in the environment. Pause 0.8. When you press a button on your remote, the device does not simply send a continuous stream of infrared light. Instead, it encodes information by modulating a high-frequency carrier wave with binary pulses. This modulation is essential because ambient light from the sun or lamps also emits infrared radiation continuously. Without this specific pulsing pattern, the television receiver could not distinguish your command signal from background noise. The remote generates a sine wave at approximately 38 kHz and switches it on and off to represent ones and zeros. Imagine a steady hum that is rapidly interrupted in a precise sequence to carry data across the room. This waveform visualization shows how the binary data rides atop the carrier frequency as distinct bursts of energy. Now that we understand how the electrical signal is structured, let us examine how these signals become physical photons emitted from the infrared LED. Pause 0.8. When you press a button on your remote control, an electrical signal triggers the internal circuitry to send a rapid pulse of current through a specialized light-emitting diode. This component is designed not to produce visible illumination, but rather to emit photons within the infrared spectrum, which lies just beyond the red end of the human visual range. The mechanism relies on electron transitions within the semiconductor material, where energy drops release discrete packets of electromagnetic radiation at a precise wavelength around 900 nanometers. Unlike a standard flashlight bulb that glows visibly to our eyes, this infrared LED emits light that remains completely invisible during operation, while carrying encoded data pulses. To visualize this distinction, imagine observing the device under normal lighting, where you see no glow, versus viewing it through a digital camera sensor, which captures the emitted infrared beam as a bright white line extending from the emitter tip. This specific conversion of electrical energy into non-visible photons allows the signal to travel without creating visual interference or distraction for the user during operation. Pause 0.8. When you press a button on your remote control, the infrared light emitted by the LED must travel through the air to reach the television receiver. This transmission relies entirely on line-of-sight propagation, meaning there cannot be any solid obstacles blocking the direct path between the emitter and the sensor. Unlike radio waves that can penetrate walls, infrared photons are absorbed or scattered by most common household materials like wood, plastic, and drywall. Consider a scenario where you place a coffee table directly in front of your television. This object creates a physical barrier that interrupts the photon stream before it arrives at the sensor array. However, signal integrity can sometimes be maintained through reflection if light bounces off smooth surfaces like walls or ceilings to reach the receiver indirectly. The effectiveness of these reflected paths depends heavily on surface reflectivity and the angle of incidence relative to the receiving photodiode. Consequently, your viewing range is strictly limited by the geometry of the room and the presence of intervening objects that absorb or block the infrared spectrum. Pause 0.8. When you press a button on your remote control, the television sensor must distinguish that specific infrared signal from all other light sources in the room. The photodiode acts as a specialized filter designed to respond only to wavelengths around 900 nanometers, while ignoring visible light. This selective sensitivity occurs because the semiconductor material within the diode has an energy gap that matches infrared photons, but not higher energy visible photons. Imagine sunlight streaming through a window containing both red and blue components. The photodiode remains electrically silent to this broad spectrum of visible radiation. However, when the remote emits rapid pulses at its designated carrier frequency, the diode generates a corresponding electrical current that mirrors those bursts. This filtering mechanism ensures that ambient lighting conditions do not trigger false signals or interfere with the intended command transmission. Once this isolated signal is converted into an electrical pulse train, it proceeds to the decoding circuitry for further processing within the television system. Pause 0.8. When you press a button on your remote, the television system begins decoding that signal through its internal microcontroller. The infrared receiver sends an electrical pulse to the main processor, which reads the unique binary code embedded in each transmission. This code acts as a digital instruction set, telling the device exactly what action to perform without ambiguity or guesswork. For example, if you press the volume up button, the processor identifies the specific sequence assigned to that command and routes it to the audio subsystem. The microcontroller then executes the corresponding function by adjusting voltage levels within the speaker circuitry to increase output intensity. This entire process occurs in milliseconds, ensuring immediate feedback between your input and the system response. With the signal fully decoded and executed, we now examine how different devices maintain unique identification codes for their respective remotes. Pause 0.8. The remote control functions as a bridge between human intent and electronic execution. It converts physical pressure into electrical signals, encodes them for transmission, and emits them as infrared light. The television receiver then decodes these pulses to execute commands.